Hello, good evening, everybody. Can you hear my voice? If you can hear, please type yes. Can you hear my voice? Hello, is it working? Can you hear my voice? Okay, can you see the screen? Tell me, what do you see? Okay, which chapter is it? Okay, fine, that's good. Now, before we start, I hope to get some feedback from you. Uh, do you have any problem with the use of this Blackboard and the online teaching? Do you think it's smooth, or you have got some problem? Could you give me some feedback? Any problem with the Blackboard learning? So one is okay. What about the others? Please note that the video for lecture and tutorial is available for your reviewing from the Blackboard. So you can pick up the video, right, for the last week, 18th of February. If you want to review and rewind the tape, so you can go to the Blackboard, okay, and download the video or online video for reviewing, okay. That should be kept under the lecture stroke video folder, right? So you can find the video and review, okay. Tell me, what is your comment on the online learning? online learning. Are you happy with that? Are you happy with the online learning compared with the conventional classroom teaching? Any feedback? Are you happy with this mode of learning? Or you prefer the original conventional classroom teaching? There will be only voice over PowerPoint for your review for chapter 1. So anyone give me feedback? Are you happy with the online learning? Do one. We have 14 of you here, right? So let me know. Are you happy with the online learning? No comment? Anyway, we will start our lecture in this evening. Okay, chapter 4, lateral earth pressure. So can you hear my voice, all of you? Yes or no? Okay. Okay, chapter 4, lateral earth pressure. Now, at the end of this chapter, you should be able to quantify the effects of lateral earth pressure. In other words, the horizontal soil pressure acting on the vertical structure like retaining walls. And you should also be able to calculate the lateral earth pressure and the total force acting on the retaining wall using the Rankine earth pressure theory, a very famous and very old theory of earth pressure that nowadays we are still using it. at this figure or the bottom corner of this slide. You got a retaining wall here, and then you have to retain a very great height of soil. In Hong Kong, we have very common situations like that because in Hong Kong we are short of piece of land, so we have to build our building right, along the hill in the mountains area. So you got to make a very vertical face here, a vertical cut there, and then you get this piece of horizontal level ground surface, and then you can build up your building structure right just next to this retaining wall. So that's a very common situation in Hong Kong, right? We have to cut the soil, we have to cut the slope, right, in order to obtain horizontal pieces of land where we could build a building. So under this situation, in this scenario, the retaining wall will be acted by a large air pressure behind the wall. The pressure will push the retaining wall outwards, right? So that will create very trouble, very troubles, or even some disaster uh, in the design life of the building structure. If the retaining wall overturns, right, topples over, or even sliding towards the building, now that will be a completely a disaster, right? Engineering disaster. So we have to prevent the soil move, right, the retaining wall out of it. So that's why we have to learn about this topic, lateral air pressure. Now, the retaining wall could be either, right, remain at rest here, right, at rest, so at rest, or it move out, move out. Okay. Now, if the force now is acting in a reverse direction, so the wall could be moved in. Right? Say if this force is very great, you got a very great force here. Okay, so this wall may move in, right? So it's move in and out, or at rest. So there are three situations: at rest, okay, going out, or move in. Okay. Now, if that is moving out, that is moving out, we call active, and that is passive. Okay. Now, consider a soil element. This soil element. Consider these soil elements. Now, for this element, there will be two types of stresses in terms of direction. The sigma is that is the vertical, right? The vertical stress, and the other is horizontal. But for geotechnical engineer, we always call these stresses lateral. Okay, lateral. 橫向 lateral stress. In other words, for any point below the ground surface, there are two types of stresses. The first one is the vertical stress, sigma z, and the horizontal stresses, the lateral stress, sigma x. Now, the ratio between the horizontal stress, so horizontal, and the vertical, the ratio of the horizontal stress to the vertical stress is the lateral earth pressure coefficient. Okay, lateral earth pressure coefficient, sigma x over sigma z. Look again at the retaining wall here. This soil element, right here, under the vertical stress and horizontal stress, well, because of the, the sigma x is equal to k times vertical stress, right, or sigma z. So k times sigma z will give you the horizontal stress. So the horizontal stress is equal to the k naught times k naught times the vertical stress. Okay. Why is k naught at rest? So we denote that earth pressure coefficient as k naught. So it's not going, the wall is not going out or in, but remains at rest. So that's the k naught. So let us recap, right? For any vertical stress, if it is at rest, the horizontal stress or the lateral stress will be equals to k naught times the vertical stress. Because we are very interested in the lateral earth pressure, so you have to calculate the sigma x. There is an important assumption behind this earth pressure theory. The rigid wall assumption. We assume the wall is very rigid, so it remains a a single and solid body, which you cannot bend it, right? So the wall will remain is rigid during the movement. So you can see the whole wall is going out. So that is active pressure, right? Active pressure. And it is moving inwards, right? So that is passive, 被动. Okay. And here, so it's, if the ball move inwards, it gives you the passive condition. If it's move out, so it will give you an active state, active state. Now, in excavation, suppose we are going to do some excavation here. Say, if we want to construct a basement, if we drive this wall or we construct this wall, what will happen? Because the wall is moving out. If the walls move out, means the soil will go out, right? So the soil will be lost here. So there will be subsidence or the settlement. in ground surface. And what about if the wall is moving in the passive condition? Because the soil will be pressed inwards. So this soil, the ground at the ground surface, try to go up, right? So the soil, because the soil is lost here, so the soil, right? Okay, so there will be increase in the level of the ground surface. So what we observe is not settlement, is what? Upheaval. Upheaval of ground means the ground surface is going up. It's completely a reverse of the settlement, right? Settlement means the ground level will go down, and upheaval means the ground level will go up. Of course, the movement of the wall in the slide, in the last slide, shows the the conceptual illustration only. Assume it's a rigid wall, right? It's going either towards the left or to the right, or going out or move in. So the rigid wall here, sorry, the rigid wall in fact only translate. But in reality, the situation is much more complex. Suppose that is a ship power. What is steel ship piling? Steel ship piling, and you got what here, right? The ground surface. You got the ground surface, and you got a props, right? Prop. What will happen? We have this lateral earth pressure here acting behind the wall, and because ship pile is not a rigid wall, it's a what? It's a flexible structure. It's a flexible material. So it's a flexible wall. What will happen? Well, the shake way, the ship pile, right? Under the lateral earth pressure may deform. It's not a rigid wall, it's a flexible wall. Now that will be very complicated for the soil pressure calculation. But anyway, uh, we will talk about uh, there will be some simplified approach to solve this flexible wall problem, right? Now, here is the movement. Movement, okay? If the wall moves in, so that's the in, and that will be out. If the wall moves out, so that is the active pressure, right? So on the right hand side, because its wall is moving out, so that's active. And here, if that is moving out, that is passive, right? But here, It's not either going out or move in, so that is zero movement. So that is what? At rest here, right? Because there will be no wall movement. Now, take this graph. If the wall is trying to move in, so you can see here, so the wall is going to move in. Now, as you can see here from this figure, it requires that it has to move for a long deformation before you come to this K value, Kp. You have K naught, the earth pressure coefficient at rest, right? And then we will talk about if it's active, you have a Ka and you have a Kp passive. Okay, you have got three cases. So from this graph, you can see you need a very large deformation. In other words, the wall have to move in for a quite good distance before it can develop the Kp, the passive pressure. And on the other hand, on the left-hand side, this movement is very small. So you need a very small deformation that will give you a full active pressure. In other words, if the wall here and here, right? So you have to move quite a lot to develop as a ground surface, large delta, right? To give you the full passive pressure. On the other hand, for active, here, you need a very small movement. So you need a very small delta, small, to develop this full active pressure. Okay? So that is the very interesting observation on the degree of the deformation to develop passive or active pressure. For active, you need very small movement. But for passive, you need to displace a quite a good distance of deformation before you can get the full passive pressure. So that is the interpretation of this graph. Okay. So is that okay? So is my explanation clear? So do you understand what I have been talking about, the active and the passive pressure? Only one is clear. What about the others? Can you get the physical meaning of the passive and the active pressure? What about the others? Are you okay with my lecture? Okay, let me continue. Now here comes the calculation. What's gamma? That is the soil, right? Gamma is what? Unit weight of soil. Unit weight of soil, okay? So what is the units? Kn per cubic meter, right? In other words, for 1 cubic meter of soil, it weighs gamma Kn, say 20 Kn per cubic meter. So for each cubic meter of soil, it weighs what? 20 Kn or 2 tons, right? 2 tons, 2 metric tons. In concrete, it weighs 2.4 kN. Okay, so concrete is heavier than soil. Okay, now we have got gamma, right? The unit weight of soil. Now, if the retaining wall is up to h meters high, that's the height of retaining wall. You know RW, retaining wall, is h. So what is the vertical stress here? Now take this element. What's the vertical stress here? Say sigma V. Sigma V equals to what? Like the water pressure, right? Gamma H or rho GH. Rho G is the gamma, right? Rho is the density. Gamma is the unit weight. So for at a certain depth below the ground surface, the vertical pressure will be equal to gamma H, right? And what's the horizontal stress? What's the horizontal stress of the lateral air pressure? Remember, it's equal to K times sigma V, right? Here we got the active pressure. So it's equals to Ka gamma H. So we got Ka gamma H, okay? So that is the here, right? In other words, if you increase H, the active pressure also increases linearly, okay? So that should be a straight line. So the pressure is directly proportional to the depth of the soil, okay? So we have done the calculation for the active pressure. Of course, you may ask, then what is the value of Ka? Now, we will come to that later, okay, Ka. In the meantime, that is a value, right? A value. It depends on the soil properties. Now, what about for the soil in front of the retaining wall? Here, we have this, small h. Again, you get the vertical stress here, what? The gamma h, small h, right? Is the vertical stress here. And you have to multiply Kp, right? Kp times the sigma v to give you the passive pressure. So Kp times gamma h. So that is the passive pressure, right? Again, it increases in a linear manner. Okay, greater the depth, the passive pressure is greater in a proportional manner. So everything is linearly increasing. So you got the triangles, right? So the pressure diagram always are always the triangles because they are linear, because the pressure increases linearly with the depth. Okay, that's the complete picture for the retaining wall here. On the left, you have the passive pressure. On the right is the active pressure. Now, can you imagine how does this wall moves under the soil pressure? So we believe the retaining wall is going out here, right? And then here, right? So it's out. That's why it's active pressure, right? Behind the wall. What about here? Because the soil, the wall here is going out, or in terms of the right hand side, the soil let the wall move in, right? Move in, right? The footing, right? The footing here is moving into the soil. So that is passive. Here, the soil is moved out. So that is active. Here, the soil is moved in, right? So it's in. So that is the passive pressure. So is that clear? On the right hand side is the active pressure. On the left hand side is the passive pressure. So the active pressure is balanced by the passive pressure in order to make the retaining wall stable. If the active pressure is greater than the passive pressure, then the retaining wall is going to slide right towards to the left. So that could be a very big engineering trouble, right, in geotechnical engineering. If the retaining wall is going to move, now let's take a look at what about for the pressure at rest. Here, pressure at rest. So K naught, right? K naught, everything is at rest. So that's K naught. Again, we have the here, right? K naught times the gamma h. Okay. Now here you have this green triangle, right? Now, for a pressure, a triangular pressure distribution, you can work out the total force. So that's the total force. The total force, total earth thrust, total, is equal to the area of that green triangle. Okay, so what's the area of triangle? The base, K naught gamma H, so that's the base, times the height divided by 2, right? So that is the area of the triangle, the green triangle. So eventually you get 1 over half times K naught gamma H squared. Okay, this equation. And what about the position of that force? The centroid for a triangle should be at the 1/3 of the height above the base, h over 3. So that is the a typical analysis for the retaining wall. If it is at rest, we have the complete analysis here, right? For a retaining wall where the earth pressure is at rest. Of course, what about for the earth pressure at active state? It's not much different, except that you replace the K naught by Ka, right, to give you the air pressure in active state. The soil at this at rest state is in elastic equilibrium. It's given by this equation. P naught, the lateral air pressure at rest, is equal to K naught times gamma H. Right? K naught is the coefficient of air pressure at rest. Gamma is the unit weight. H is the height of the wall. And the total force, or the earth force acting behind the wall, will be equal to K naught gamma H squared divided by 2. Now, you have to pay attention. Here, what's that? Per unit width of wall. Now, let me check the unit. K naught is dimensionless. It has no dimension. Right? Just like A equal to pi r squared, right? The area of circle is equal to pi times radius squared. That is dimensionless. Here, on the left-hand side is meter square, and right-hand side, r in meters, r square means meter square. So pi should be dimensionless. Again here, K naught is dimensionless. But what about here? Kn per cubic meter times what? Meter square. So that will give you Kn per meter. What does that mean? It means that, if that is a wall, the retaining wall, okay, and here is the P naught, okay, it means that what's the force? And that is the H, and that is 1 meter here. So for every meter length, for 1 meter length of wall, P naught give you the force, right? How many kN acting per meter length of the wall. So that is the meaning of this kN per meter. Kn, okay, and here per meter, per meter. So you understand the meaning of this P naught? Kn is the force acting for every meter length of the wall. And the position of the P naught is 1/3 of the height, or 1/3 of the height from the base of the wall. We come to the calculation of the K naught. Now, K naught is the coefficient of the, of the soil at rest condition. It's equal to 1 minus sine phi. Phi is the angle internal friction of soil. Well, we have talked about the, the cohesion and the angle internal friction in the last chapter, chapter 3, the shear strength of soil. Soil, you have two important parameters, right? The cohesion, and the friction angle. Remember that? Very important graph. You have the sigma, and you have the shear strength. So that is the C, and that is the angle internal friction. For this soil, you got phi, so the K naught is given by 1 minus psi phi. 1 minus psi phi. Okay. But here, the equation applies to loose sand. What about if the sand is very dense? Then you have to apply a correction factor. Quite a very complicated equation. Gamma D. Now you need not to memorize it. Right? Just know something about it. That's good enough. Gamma D is the actual compacted dry unit weight of sand. It means it's a dense density. And the denominator is the loose density. The density of sand in a loose state, while the denominator is the density in a dense state. So you have to add these parameters, right, into the 1 minus sine phi. You have to plus it. That is the correction factor, right? The right hand side is the correction factor for the density of the soil if the sand is in a dense state rather than a loose state. But here you got loose state only, and you got here the dense state. Okay, that's the correction to be applied to work out the K naught for sand. Take a look. If that is a retaining wall, and you got a ground surface here, and then you have the active pressure acting behind, say that's the active pressure. If that is H, so that is Ka gamma H, right? But now we have groundwater table, GWT, groundwater table. So not only these, the soil pressure acting on the wall, but also there are water. Water give you the hydrostatic pressure, the water pressure, also acting on the wall. So you have the water pressure. Okay, so that is, if that is, say, if that is small h, so give you gamma W is the unit weight water times h. So the total pressure, the active pressure, lateral soil pressure, plus here pore water pressure. So you got two pressure diagram, one coming from the soil pressure and the other comes from the water. Okay, now I want to explain a little bit further about what's the pores. Say a certain depth, you got the soil particles here. As you may remember, in our last chapter, I have talked this about before, the soil pressure. And here, at a certain depth of the soil, the ground level, you got the, that's the, the pore, the voids, right? The air space between the soil grains, the soil particle. And in the pores, in the void, you have completely filled up with the groundwater. And at a certain depth, certain water depth, this water pressure could be very high, right? Pore water pressure. Okay, the water pressure try to, attain normal to the soil particle surfaces. It tends to pull the particle apart. So remember that stress, it will decrease the actual soil stress here by this pore water pressure. In other words, here, originally, without water, this sigma could be very high. But because under the action of the pore water pressure, it effectively decreases the contact stress here. That is the effective soil contact stresses. Suppose if that's 100 minus 30 equal to 70. In other words, without water, the, the soil contact stress could be up to 100 kPa. But because under the pore water pressure at that water depth, it will decrease by 30. That will give you effectively the contact stress are touching each other at a 70 kPa only. Okay, so that explains the pore water pressure for a retaining wall. So again, is that clear to you? You understand what I'm talking about? I hope you are not slipping. I need feedback from you, you know. I'm not talking to the void. I'm not talking to the air. I'm talking to you, right? Because I cannot see your face, so I don't know whether you understand or not. So you have to give me some feedback, right? Good, not slipping. Okay, we'll continue our lecture. By the way, I hope my, the writing could help you to understand the lecture notes, right? Now, in this slide, first of all, we are talking about the retaining wall at rest condition. So it's not going out or in. We have talked about the effective stress concept. Okay. Now here, the point here, that's H1. So what is the stress here at point E? Here, very easy, right? That is gamma. That's the gamma. The unit weight of solid is gamma. So gamma times H1, right? So you got what? K naught gamma H1. So now you may ask why there are two kinds of diagrams. On the left, it is the effective stress, and that's the total stress. Okay, so on the left is the effective stress diagram, and on the right is the total stress diagram. Now, because at the depth h1, talking about at point E, there's no water at all, right, about that point. So the U is equal to 0. So sigma dash equal to sigma. So the total stress is exactly same as the effective stress because there's no water here. What about for the point G at the bottom, right? At the bottom here. We want to work out the total stress first. Here, right? What's the total stress? Now here, what's the total stress up to this point and this point? Because you have gamma here, and the effective stress here. What's the effective stress? So you have to use this equation. The the total, the saturated density minus the gamma W. Gamma W is the unit weight of water. You have to minus it. You got to the effective unit weight without water means. So you have to minus the unit weight water. So here, coming back to this diagram here, right? Above is gamma H1. So you got the gamma H1 here. And then here, right, you have what are this? What about here? The gamma plus gamma dash times H2, right? So you got this. So gamma H1 plus gamma dash H2, because that is H2, right? The lower part is H2, that's H1, that's H2. So the effective stress is equal to, gamma dash times H2 plus gamma H1. Now that gives you the effective stress only. So you have to plus the U, right? So what's the U here, right? The water pressure at the bottom of the wall. Very easy. Gamma WH2, because that is H2, right? So gamma water times H2. So plus that. Now this will give you the total. So on the right hand side, it gives you the total stress, right? Because you have added the pore water pressure there. So this diagram, gamma H1, sorry, K1 gamma H1, and then the whole thing here, right? The K naught times bracket gamma H1 plus gamma dash H2, and that's the effective stress, plus gamma W H2. Now that will give you the total stress. Effective stress, very simple. Here, K naught gamma H1. What about here? Okay, coming down, then you have gamma dash H2, because here you the gamma dash. Here's the sorry, that is the gamma, right? So here gamma H1 plus gamma dash H2, because here's the effective stress. So you have to work to use the effective unit weight of the soil. If you add these two diagrams, so the effective stress distribution diagram plus the pore water pressure diagram will give you exactly the same as the total stress pressure diagram. Okay, now let's take a look on the work example for the earth pressure calculation. Example 1. Here, now you are given the soil data, right? You got a water table 1 meter below the ground surface, and the soil here is dry, right? This dry, and here you got wet soil and the dry soil, because below the groundwater table, every soil there is wet. So you get the gamma SAT, What does that? SAT. What's SAT? Saturated with water. Saturated soil unit weight. Weight of soil. It's 19.5. Okay. kN per cubic meter. And friction angle, 32 degrees. Now, you have to think about, is the retaining wall at rest or in the active or passive state? Let's take a look there. Low lateral movement, so that is at rest, right? K naught. So K naught is equal to what? Because loose end. So K naught equals to 1 minus sine phi, right? So K naught is equal to 1 minus sine phi equals 1 minus sine 32 degrees, right? What's that? 0.47, right? 0.47. 0.47. Okay, then we can work out sigma 1. Sigma 1 equals to what? What's the vertical stress there? 5 times 1, right? And what's the pressure coefficient? K naught 0.47, right? 0.47, right? Times 17.5 times 1. That gamma H, and that's the K naught, right? Now that gives you the sigma 1. Now what about sigma 2? Now sigma 2, sigma 2. What's the effective stress there? Equals to what? What's the vertical stress here? Sigma 2. Sigma 2. What's the vertical stress there? Again, 0.47 times, sorry, vertical stress first. What's the vertical stress here? 17.5 times 1, right? You got this point here. And then you come to this point, plus what? What's the effective stress? Effective unit weight here. What's the unit? 19.5 is the saturated minus 9.81, right? That is the what? Gamma dash, right? Gamma dash equals to 19.5 minus 9.1, right? Times what is the depth here? What's the depth? That's 1 meter. The upper part is 1 meter. What's the lower part? 2 meter, right? So times 2. Okay. So that is the vertical stress. Again here, right, let me recap. Here, 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 17.5 times 1. And then we come to next layer. The effective unit weight, 19.5 minus 9.81 times 2 meters, right? And then the whole thing times what? 0.47. That is the vertical stress times the K naught. 0.47 is the K naught. Now that gives you the sigma 2. Okay. So what's sigma 1? P1, 8.25, right? So 8.23. So 8.23 kPa. And more sigma 2. Okay. Okay. That is our sigma 2 dash, right? Exactly the same. And then what's the total pressure? You have to add up the pore water pressure, right? So if you want to work out the sigma 2, you have used the sigma 2 dash plus what? Plus water pressure. Water pressure is equal to 9.81 times 2, right? So that will give you what? Exactly this one. 37, right? 37. Okay. So you just okay here sigma 2 dash, right? Plus the pore water pressure. That's the U. So when you draw the total pressure diagram, total pressure diagram, sigma, right? So at 1 meter below the ground surface is 8.2, 8.23 kPa. At the bottom here, 37 kPa, right? So what is the earth thrust, or the earth or total earth force? Earth thrust means force. What's the total force? Or the soil, whether you are talking soil or earth, it's just the same. Soil thrust P1 is equal to what? The area of the yellow triangle, right? So 8 point, sorry, 8.23 times height divided by 2, right? So equal to 4.115 kn. Remember, per meter length, right? per meter length of the wall. And what's the area of the blue trapezium here? It gives you the total earth thrust acting on the lower 2 meters of the wall is equal to, where is it? The area of the trapezium, right? Divided by 2 times 2, right? The area of the trapezium, right? The B plus B times divided by 2 times H give you the area of the trapezium. So, okay. So the area, and then that is the, the area of the yellow triangle, and that's the trapezium. Right? This area of the, the yellow triangle. Now that will give you a total 49.3 kN. Okay. In other words, P1 plus P2, right? Give you the total soil thrust acting on the wall. (49.3 kN per meter length). Is that okay? It's not that difficult, right? Any question? No question. Okay, that's good. Okay, now we come to the Rankine earth pressure. Now, Rankine pressure is a very old theory. This guy is so famous that in now in UK, every year they arrange what we call the Rankine lectures. Now, the top soil expert, right, or the geotechnical scientists or engineers will be invited. If he or she deserve that kind of great honor, he will be asked to present Rankine lecture, right, ranking lecture on the geotechnical engineering topics. Now, that is a very important lecture. If you are if you are invited to whether to attend or to present, that means you are a very top soil expert or geotechnical expert in the field, right, all over the world. So that this guy have introduced to us his theory of earth pressure. It's one of the earliest theories in during the in calculating the lateral earth pressure. Now there are some assumptions behind this ranking theory. First of all, okay, no adhesion between the wall and the soil. It means that, okay, here, now if the wall is going to move out, so that's active, right? Active state, active. So this, there's a piece of the wedge of soil, right? Soil wedge is going out together with the wall. But here, between the wall and the soil, the friction is equal to 0. So there's no adhesion of friction. At the interface between the wall and the soil and the vertical soil surface, there will be no friction developed. Of course, that is a very oversimplified assumption. Right? In fact, in reality, we do have the friction or the adhesion between the soil and the wall. So that is the limitation of this theory. It's not true in real application. And the failure is assumed to occur in the form of that sliding wedge, as I have shown you in the previous slide, the soil wedge, the triangular piece of the soil mass. Now it is going to occur along an inclined plane of failure, an angle which is function of the internal friction. Now coming back to here, now that statement talking about this, the alpha, that is this. This is the plane of failure because the soil wedge is sliding downwards, right, against the lower part of the soil. This angle, alpha, so the alpha, right? Alpha depends on the phi of soil, okay? The angle internal friction of the soil. And again, the lateral earth pressure is assumed to be very linearly, right? Varying linearly or in proportional to the depth of the wall. In other words, you have the soil pressure diagram in form of triangles, right? And also the resultant force, the soil thrust, is assumed to act at 1/3 of the height of the wall. Well, we have demonstrated, right? The centroid of the triangle is always at the 1/3 of the height from the base of the wall. And the direction of the resultant force is parallel to the slope of the soil of the backfill surface. Now, let me draw a diagram to illustrate what does that mean. If you got a retaining wall, yeah, right? Sometimes you do not have a a flat surface. Just like in Hong Kong, we always have a sloping angle. So if that is beta, the direction of the resultant assumed to be parallel to the slope of the soil at the backfill surface. Okay. So if that is the failure plane, it means that the resultant force, okay, so that is the resultant force, the P, right? Is parallel to the sloping. So again, this is that's also beta, right? Just like that. So it's parallel to the sloping surface. So in other words, this is parallel. So that is parallel, right? Parallel to the slope of the sloping surface. Well, that's sensible, right? Here, if here is the, the, so if that is not, that the ground surface is not sloping, so it's parallel, right? Okay. So if the sloping surface here, so this is also parallel, right? So always parallel. So that's P, okay? The P is parallel to the sloping surface. P is the resultant force or the total soil thrust. Okay, now we use the Mohr circle to demonstrate the active state of the soil element. Now consider here this soil element. Okay, now follow my pens, right? Throughout my whole explanation. First of all, you got the sigma naught vertical stress. Okay, sigma naught dash is the vertical stress. And then you have the horizontal stress. But horizontal stress, you have either, you know, free state at rest, okay, that's K naught, and then active, which is Ka, and then passive, right, Kp, right, Kp, passive. Now, first of all, we are talking about the K naught first, right, at rest first. Notice that at rest means sigma naught dash, and then the horizontal stress is equal to what? What? Equals to K naught times, because K naught sigma naught dash is the vertical stress, so you have multiplied K naught, right? Give you the horizontal stress. So in other words, for the at rest here, you got K naught sigma naught dash, and then K naught times the sigma naught dash. So that is the point here. Here, right? Here is that rest. So it's the K naught sigma naught dash, right? The horizontal stress. And the vertical stress here. Okay? So you draw this circle, more circle, because you got the, the sigma naught dash is the vertical stress, and because at here is the principle, all the shear stress equal to 0. So sigma naught dash and the shear stress equals 0. So you got this point. And the horizontal stress, you got this K naught times the vertical stress, and shear stress equals to 0. So you got this point. And with these 2 points, you can draw a small circle, right? So the red circle represent the at rest. So everything in red is the at rest, okay? Now, we come to the active state. Now, what is the active state? Perhaps I should say at rest, not sigma, not dash, okay? So for active state, okay, okay. So for the active state, everything in black, okay? Everything in black, active, everything in black. So sigma naught dash, and the horizontal stress equals to what? Active Ka, right? Sigma naught vertical stress times the Ka. So now here, sigma naught dash, okay? What about the active? Active equals to here, okay? Ka times sigma naught dash, okay? Now you got these 2 points, right? So you draw a more circle. that's active state. Is that okay? So you got, two states here. If the retaining wall remains at rest, you got the at rest condition. So you have the Moore circle in red here, right? But if the wall is allowed to move outwards, so that wall is in an active state. So you got this Moore circle in black. Okay. Now, if that Moore circle just touches, sorry, this straight line. What's this straight line? Okay. Shear strength equals to C plus sigma tangent phi, right? In other words, if this small circle touches this point, touches this straight line, it means here you got the soil fail at this point. Now, what's the failure plan? If you measure these 2 theta, it is counterclockwise or anti-clockwise 2 theta, okay, to the sigma naught. So you can here's the sigma naught, the plane where the sigma naught, anti-clockwise theta, right? Because that is double 2 theta, and here you got theta. Because the at that point D, right? At point D, it touches the failure or more column failure line. So in other words, you got at the angle theta, right? Measure anti-clockwise from this horizontal plane. You got the failure sliding over each other. So that theta is the angle of the failure plane. Whenever the Moore circle touches that important string envelope, it will fail because the soil cannot exceed the stress in the soil cannot exceed that string. So whenever the small circle, right, touches or even pass through it or cut across it, that's impossible. The soil will fail first, right? So that is the limiting stress that the failure plan could take. In other words, here, if you have that, the movement or the active state of soil, then the wall, right, will fail, or it will means it will sliding, right, to go out and fail, and that, you know, that is your failure angle. So that soil wedge here, right, the soil wedge here, the soil wedge here will fail by moving out, go out and fail. What's the angle? The angle is equal to here 2 theta. Okay. Now, if you can work out what's the theta, what's this angle? That's right angle, 90 degrees plus what's that? Phi, right? So you got this equation. 2 theta is equal to 90 degree plus phi. The sum of interior angle is equal to the exterior angle, right? So by simple geometry, you work out theta is to 45 degree plus phi. dash over 2. Well, suppose if that is 30, right? In Hong Kong, we have common that we have that common angle of internal friction 30. It means that theta equals to 45 plus 30 divided by 2 equals to what? 60 degrees. So you have the saw wedge at 60 degree to the horizontal will fail. Phi is the basic property of a soil. So you got this, the active state analyzed by the Moore circle. Okay. What about here? What about if the retaining wall here, right? Now, if the retaining wall is moving out, what about here? The soil element here. We take out this island. Sorry. Okay. Okay. If that is this sigma naught dash, right? Of course, this sigma naught dash is very small, right? If that is h, so that is gamma h. Now, what about if the ground here is the passive, right? What's the passive? That means the wall is moving towards the soil. So you got the passive state, right? What's this? What's this stress here? Sigma p is equal to kp, right? Times gamma h. That is the passive pressure coefficient. Now, if that is, sorry, okay, that is C, that is phi, right? Phi, cohesion and the angle internal friction. Now, here, suppose you have a here, right? Here is this, here is the sigma naught dash, right? Sigma naught dash. So you got, for this plane, you got this point. Now for this one, what about here? You got what? Sigma p. Sigma p could be here, right? So that is the sigma p. Sigma p. Now you can draw a circle, more circle. Okay. Now because the more circle does not touch this, you know, shear equal to sigma sigma tangent phi, right? No failure. In other words, this soil do not fail. But what about if the sigma p is very large? Suppose it's very large here, right? Very, very large. What will happen? So the sigma p will be moved, right? Much here on the right hand side, right? Because sigma p is very large. What will happen? If you draw the Mohr circle, right? That means it will fail. Fail will occur, right? So the soil here will be, right? The soil upheave, right? Will go up. So it's a typical passive failure by passive failure. Okay? If the sigma p is very large, because Kp could be very large, then it will fail. The soil will fail, the passive failure. Okay? Is it good enough for you? Is that good enough for you? Or you are pretty fed up with my lectures? If you have taken your dinner, then you will be fed up by my material, right? By my lecture material, and you have no appetite for your dinner. Then do you follow with my lectures? Yes or no? Oh, that's good. Now I will talk about a very common incident. Why when we are digging a tunnel, the tunnel roof will always fail. Now it's a very interesting topic. Now I will use the Mohr circle to explain, right, why this failure will occur. Okay, it's quite interesting. Okay, here we go. Here's mountain, right? 大帽山. That's a tunnel. Okay. Now, before consider this point at the top of the, at the top of the crown of the tunnel. So, can I withdraw? Now, before we excavate this tunnel, consider this soil element. Now, original, that's the vertical stress, and that is the horizontal stress. Okay. So the vertical stress, gamma, say here, right? Z, right? Gamma Z is the vertical stress, overburden weight on the top of the soil mass here. Okay. Now we draw the, the Mohr circle. Now suppose the strength of the soil there is along this line. Remember, C plus sigma tangent phi, right? Give you the shear strength. Okay. Now, here, for this point, for this plane, shear stress equal to 0, and you got what? Here, point here, right? Sigma V, 0. Sigma V, okay. Shear stress always equal to 0, right? Because we are considering the principal stresses. Okay. Now, for this plane, here, right? What about for this plane? So you got this point here, right? Sigma H. Okay. That is sigma H, right? Okay. Now you draw the Mohr circle. So it does not touch the envelope, right? The Mohr Coulomb envelope. So no failure. So before the tunnel is built, of course, soil never fails, right? Because it's well below the Mohr Coulomb envelope line. But if we build the tunnel, so what will happen? Now we build the tunnel. We move this soil out, right? The soil out. Now consider we now build the tunnel, right? Now what will happen? Here, the soil mass, here, right? Now what's the vertical stress here? 0, right? Because that's the air, that is the soil. So the sigma V suddenly become to 0. What will happen? So it comes to this point, right? 0, right? Okay. And the horizontal with that, we draw a Mohr circle, right? So you can see here, because you have excavated the soil from the tunnel, that the sigma V equal to 0. The sigma V equals suddenly come to 0. That the whole Mohr circle will try to move left hand side, right? In other words, it's much closer, right? to the failure line. Okay. In other words, you are marginally failed because of your tunnel construction. What about if you have that, right? And then you have the Moore circle, right? Okay. And then when you do the excavation before tunneling, right? But after tunneling, you could simply, right? So failure of the tunnel roof, okay, after construction, after excavation, because you move beyond, right, the more Coulomb envelope, so you will fail here. So is that okay? So you want a black here? You want a black for a tutorial? Okay, let's take for 10 minutes. Okay, welcome back to our tutorial. Now, before I start my tutorial, I have to say a few words for your submission of the tutorial. Now, up to now, I have received about only 10 to 11 submission from you. So there are some other students who haven't submitted the assignment one. Now, today is the deadline for the submission of the assignment one. So please do submit your assignment to me as soon as possible, right? Within today, okay? Now, in returning the assignment, I want you to submission assignment. First of all, the first criteria in single file copy, right? In PDF format, please. Now, you don't hand in your assignment in separate file because I have to, to combine them all in one. Now, it will impose workload for me, right? In particular for so many students. So please combine all your solution, right, into a single file and in PDF format, please, right? And the second is the file name. The file name should be looking like that. So it's A1, assignment A1, and then your name, Chen Taiman, and then your student number, right? Okay, so first of all, the first two character means assignment 1, 2, 3, or 4, or 5, 7, and so on. And then your name and your student number. Okay? And please email it to polyu.edu.hk by the deadline. Okay? Clear? Is that clear? Okay, that's good. Now, let us take a look for some of the solution for certain tutorial problem. Now, we will exploit, right, the discussion of this assignment to illustrate how the theory could be applied to the problem solving in geotechnical engineering. Now, under this topic, shear strength of soil. Now, let us take a look for the first question first. Okay? Now, Now we are looking for this slope. This is a slope. Now you got the, the point here, A. Okay. Now part A, you are asked to evaluate the shear strength at the point A. Shear strength at the point A. If the groundwater table is at level B. So here we go. So that's the groundwater at B. Okay, so part A. Now, if you want to work out this shear strength at A, you have to use this equation, right? Very famous equation. So what's the cohesion? 6 plus sigma tangent 25°, right? Okay. Now, of course, when we are talking the shear strength, we are talking about the effective stress, right? Everything in terms of effective. So the effective. Now, what's the effective stress at A? First of all, what's the depth here? 9.5, right? Is it 9.5? 9.5 meter, right? So what's the unit weight? Above the ground water is 18, right? So 18 times what? 9.5, right? Now, and then you have to come to that 4 meter below the groundwater table, right? Here. So plus what? Plus below groundwater table. So 19.5 here, right? Minus 9.81. So that is the effective unit weight of soil, right? Minus 9.81 times what? Times 4 meter, right? So give you 209.8 kPa. Okay. So once you got the, you know, the effective stress at A, so you can work out SA, right? Equals to 6 plus 209.8 times tangent 25, right? It give you 209. Sorry. It give you 103.8. So is that okay? Now, if the groundwater table rises to level C, right? So here you have the groundwater table here. Right? Now I'm going to repeat the calculation. Right? It's quite similar to the part A. Okay. So I will leave the part B to you. Now let's take a look for the part C. Construct the Mohr circle envelope and the Mohr circle for the stress at the point A for parts A and B on the same plot. Will shear failure occur at the point A for both situations? Now, because we have worked out part A, so I want to work for the part A only. Okay, in part A, first of all, see part A. Sorry, part A. Now, first of all, you draw the Mohr Coulomb envelope, right? C equals to what? 6, right? And here you got 25 degrees, right? It's given, right? The soil properties. Okay. Now consider the element. The vertical stress 209.x, right? In part A, we'll work out the vertical stress. And what about the horizontal stress? Because it's given there, the K here, right? So 0.54. So here, right? Point, sorry, 0.54 times 209.8 give you 113.3 kPa. So you got the 2 points here. So one is what? So 209.8. And the other one is what? 113.3, right? That's point A. That's the A. So can you draw the Mohr circle? So since it appears that it does not touch the Mohr Coulomb line, envelope line, so no failure. Okay? Of course, you should specify it. The shear tau, that's the sigma, right? And this equation is equal to S equals to 6 plus sigma tangent 25, right? So is that okay? Okay, then we go to problem 2. Now, let me explain first, right? What does this test talk about? You know, that is a same cylinder specimen. Okay, you apply the normal load N, right? That's diameter. What's the diameter? 60, right? 60 mm. And then you apply the normal loading, normal load N, and then you try to shear it off, right? To shear. You apply a shear force. Okay, so this specimen will be shear off into 2 pieces. Right? So that is the shear strength. Right? Okay, then what is the sigma V? And what is the, the shear strength? Well, sigma V equals to the N, okay, divided by pi d squared over 4, right? Shear force, sorry, the force divided by the area will give you the stress. So say for test 1, test number 1, test 1, sigma V equals to what? 400? Because we are talking about kilopascal, so everything convert into kilonewton. 10 minus 3, and then pi d is 60 millimeter, so 0.06 meters square divided by 4, right? What will you get? 141.5 kPa. Okay. Now, what's the shear? So I've worked out 141, 141, right? So that is 141.5 kPa. What about the shear? Shear equal to N divided by, again, pi d squared over 4, right? So it's 282, N to minus 3, again, pi 0.06 squared divided by 4 equals to 99.75, okay, kPa. So that gives you 99.75, okay? So by similar calculation, you can work out the test 2, 283 here, and 212.6, right? So I will not repeat the calculation for test 3 and test 4. Now, when you draw the more Coulomb envelope, that is the S, that's Six Sigma. So the first point is what? That's 141.5. And then you have what? 99.75, right? You got this point. And then for test 2, 283, right? And you got what? Here, you got 212.6. So you got, test 1, test 3, and test 4. So you draw a straight line, right, passing through. Okay. Of course, there should be a C, right? And also phi. So when you plot the four set of data, so you get the bare straight line passing through the 4 points, and you got the intercept, right, for the shear stress axis and also the angle of the straight line. So please work out what's the C and what's the phi, right, after plot from the graph, from the plot. Okay. Now, because the assignment 2 will be given and will be given and not required for the return for the submission, I will give you the solution for this assignment 2, right? 1 week after. Okay. So you don't need to hand in the solution, but I will suggest and I will encourage you to do, right, the calculation at home, right? And then in the next week, once you have got the solution, you can compare your result against the answers. So it's a good experience for you. Okay. So any question? Okay, that's good. uh, question 3 is a very important topic for our discussion whenever you are studying the soil mechanic or geotechnical engineering, because it's a very famous test. What's the name of that test? Triaxial compression test. Now, what's that? For steel, you know this word steel bar, right? 鋼筋, So you got a steel bar there, and then you apply a tension test. That is the tensile strength test, right? Tensile test. And what about for concrete? You got a cube, right? A concrete cube, and then you apply the compression, and then you will obtain the 28 days compressive strength test, right? Is that true? Now, this is uniaxial testing. Sorry. Uniaxial test. It means the test will be performed for single axis, okay, for one axis only. But for soil, it's very different because you want to know the shear strength test. Now, what's it? When you obtain a cylindrical specimen, first of all, you have the X, Y, sorry, Y here, right? You have the stress acting not only in one direction, in two directions first. So you apply the stress in sigma X and then sigma Y, right? So in X direction and Y direction. And then you apply you apply you apply the sigma Z, okay? Sigma Z until it fails. So the specimen will fail look like that. Okay? It will fail by shear. It will shear off into two pieces. Now, so this sort of test employs the loading in three axes. So that is called the triaxial test. And also because all the stresses are in compression, so it's the compression test, triaxial compression test. Why we have to perform the testing in that way? Imagine you obtain the soil sample, right, below the ground level. Now, at that depth, that specimen, that soil, is actually subjected to the stress in three axes, not only in x direction, y direction, but also the z direction, particularly in the z direction, because you are putting up the weight of the building, right? The weight of foundation upon the soil in the vertical direction. So sigma z is very important. It's the most critical stress. In other words, in the lab test, if you increases the sigma x and sigma y, sigma x, sigma y are called the confining stress. It means that the specimen is surrounded by the stress, right? By the horizontal stress. Sigma x and sigma y are the horizontal stress, right? The left coming from the left or the right or in the front or at the back. So the stress are confining the soil specimen. Deeper the depth below the ground surface, the confining stress will become greater and greater, right? If you want to fill that soil at that depth, so you have to apply a very great sigma z. So in other words, if the confining stress is going up, if the confining stress is greater, then your sigma z will be larger. Will be required, right? Or the larger sigma z will be required to fill the specimen. To cause failure. Now, it's very reasonable, right? If you have a larger confining stress, or in other words, at a greater depth below the ground surface, the soil will give you a higher shear strength before it fails. So imagine, right? Say here, if you have a, sorry, so if that's 100, if that's 100, confining stress, what's the vertical stress to fail it, to fail this specimen? Suppose that's 500, right? Say if at Z, say 10 meter below ground surface. What about 100 meter below the ground surface? At that depth, you have the confining stress much greater, right? Say That's 500. So what would you expect the vertical stress there to fill this soil at Z, say 100 meters below ground surface? Now we believe that it could be 7,000. In other words, at a greater depth, the soil could only fill at a vertical load of 7,000 kPa. In other words, we can put our building structure, right, with the foundation at that depth. So no matter how tall is the building, at the exact 100 meter, they can resist your loading failure because the confining stress is very great there. So you see what I mean? That's why we have to perform triaxial compression tests, right, in many geotechnical laboratories for soil testing. Okay, now let's take a look for this triaxial compression testing. First of all, you have so the soil sample. Now this is water, right? Inside the tank, water pressure. Now that gives you the confining pressure, sigma 3, right? Confining pressure. Okay, and then you apply the load from the top, right? So it's going to moving down. So that gives you the vertical stress, right? Sigma 1, the vertical stress. If sigma 3 is higher, the higher the confining pressure, that will you require a higher sigma 1 to fill the soil specimen. Right? Now, whenever you apply the loading, because the soil sample could be having some water inside the voids. So when you apply the loading, sigma 1 or sigma 3, now that will increase the pore water pressure. Now that's no good because we are investigating soil behavior. We don't want the test result will be affected by the pore water pressure. We are going to look into the interlocking of the soil particle. Right? So we want to know the effective stress. So you have to provide the drainage, right? The drainage. When you apply the loading, first of all, the loading will be taken up by the water pressure. So you have to provide the drainage. So that's why in the part A, you have the undrained, unconsolidated. So you have no time given to the water escaping from the specimen. So anything to add on the loading, adding on the soil specimen, that loading could be resisted by the pore water pressure, but not by the soil particles. So that is called the unconsolidated undrained test. But that's a pretty lower quality testing because you're not investigating about the interlocking of the soil particles. Now, the best method is the consolidated drainage test. This one. Now, what's that? When you apply a loading, sigma 1, to the soil specimen, then you have to provide the drainage and time for the water, right, to dissipate or to escape, to dissipate the water pressure from the from the testing apparatus, from the soil specimen. In other words, you allow the pore water pressure, right? The effect equal to zero, right? So you anything, any loading you are imposing upon the soil specimen will be giving rise directly to the effective stress, to increase in the effective stress of the interlocking of the particles. So that is the CD test. Of course, you can also have the consolidated undrained. Again, undrained, you do not allow the water pressure to escape. Anyway, in a lot of laboratory testing, we often employ the CD test. Okay. Now, here, the confining pressure, right? Here, sorry, sigma phi. Now, what's the deviated stress? It means that this specimen, first of all, you apply sigma 3 all around, right? Sigma 3 confining pressure, right? And then you add up a certain part until it fails. So this will give you altogether one, right? From sigma 3, you add a smaller amount, give you the total sigma 1. That amount should be equal to sigma 1 minus sigma 3, right? Now, this is the deviated stress. So the deviated stress is defined as sigma 1 minus sigma 3. That's deviate, right? The amount deviate from the sigma 1. So anyway, you have the test number 1, 2, 3. So sigma 3, you got the values 69, 138, 207, and deviate. Now, can you work out the total stress? Sigma 1. Very easy, right? Sigma 1 equals to what? Sigma 3 plus deviated stress, right? So you just add up, give you what? So 69 plus 276 give you 345, right? Plus 275, 276 equal to, and then you got, right? 138 plus 328 give you 466, right? And then 207 plus 359 give you 566. So you have the now let's take a look on how to draw this small circle. Oh, sorry, it's too bad. Okay. Okay. So the first more circle, right? Sigma 3, 69, right? And then sigma 1, 345. So you draw this small circle, right? And the next one is what? 138, 138. And then sigma 1, 46, right? So you obtain another more circle. And then I don't want to repeat. You have many, so. And then you draw, sorry. So you draw the more circle, right? And then you obtain this straight line. So you can work out C and the phi. Okay? So by performing the test 1, 2, and 3, different confining pressure, and then you apply the different deviated stress. So you got 3 specimen. Eventually fail. So you got the 3 more circles here. And then by the 3 more circle, you can draw up the more Coulomb envelope to obtain your cohesion and the angle internal friction. Okay? Okay, I think I will stop here, right? And so you better try, the assignment 2 problem, right? So that you will be getting more familiar, right, with the use of more circles and also the effective stress calculation and so on. Okay? Now you need not hand in the assignment 2, right? Because they will not be they will not be counted towards your CA result, the continuous assessment result. Okay, only the odd number tutorial assignment will be required for the submission. Okay, so any questions? Are you happy with the lecture and the tutorial? Are my explanation to the tutorial clear to you? A final reminder, right? For those who haven't submitted, please hand in your assignment 1 tonight. Okay. Any question? Okay, if no problem, I will say goodbye to you. Okay.